In Section 2 of Chapter 6, we'll review real applications of the normal distribution. In this section of Chapter 6, we present methods for working with normal distributions that are not standard. That is to say, the mean may not be 0 and the standard deviation may not be 0. The key is that we can use a simple conversion that allows us to standardize any normal distribution so that the same method of the previous section can be used. This formula is known as the conversion formula, and it allows us to standardize any normal distribution so that x values can be transformed into z-scores. These figures illustrate the conversion formula from a non-standard normal distribution to a standard normal distribution. The area in any normal distribution bounded by some score of x is the same as the area bounded by the corresponding z-score in the standard normal distribution. When we want to find an area of a non-standard normal distribution, we will use this procedure. First, sketch a normal curve, label the mean and any specific x value, and then shade the regions representing the desired probability. For each relevant value of x that is a boundary for the shaded region, we will use the formula z equals to x minus mu, the population mean, divided by sigma, the standard deviation. And then this will allow us to convert that x value to an equivalent z-score. If we use technology or we use Table A, we can find the area of the shaded region. This area is the desired probability. Let's consider this example. Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Let's find the percentage of men who are taller than a specific shower head that is set at 72 inches. Step 1. Men have heights that are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. In our graph displayed here, the shaded region represents the men who are taller than the shower head's height of 72 inches. Step 2. We can convert the shower head height of 72 inches to a z-score of 1.21 by using the conversion formula as follows. Z equals to 72 inches minus our mean, which is 68.6 inches, divided by our standard deviation of 2.8 inches. And that gives us a z-score of 1.21. For step 3, we can use technology or we can use Table A2. If we use technology to find the area to the right of 72 inches, we'll find that that area is equal to 0.1123. The result of 0.1123 from technology is more accurate than the results we will find using Table A2. But we may not always have access to that technology, and so we can use Table A2 for Step 3. Use Table A2 to find the cumulative area to the left of the z-score 1.21, and that area is 0.8869. You can see that in my Table A2, the column all the way to the left are the first two numbers in my z value of 1.2. And then we go across that row to the right to the column that's labeled 0.01. And that shaded yellow number is our area that's to the left of the z-score of 1.21. Now remember, because the total area under the curve is 1, it follows that the shaded area we're interested in that we showed on our previous slide is equal to 1 minus 0.8869, and that's equal to 0.1131. So we can interpret our results as follows. The proportion of men taller than 72 inches is 0.1123 or 11.23%. So we can say that about 11% of men may find this specific shower head design to be unsuitable to meet their needs. So here are some helpful hints for those cases in which the area or the probability is known, but we must find the relevant x values. First, graphs are extremely useful in visualizing, understanding, and successfully working with normal probability distributions, so it's important to always use graphs. Second, don't confuse z-scores and areas. Z-scores are the distances along the horizontal axis, but areas are those regions underneath the normal curve. Table A2 lists z-scores in the left column and across the top row, but the areas are found in the body of the table. And 3, choose the correct left or right side of the graph. A value separating the top 10% from the others will be located at the right side of the graph, but a value separating the bottom 10% will be located on the left side of the graph. Number 4, a z-score must be negative whenever it's located on the left half of the normal distribution. And number 5, areas or probabilities are always between 0 and 1, and you can never have a negative area or a negative probability. Let's review the procedures for finding values from a known area or a known probability. First, sketch a normal distribution and enter the given probability or percentage in the appropriate region of the graph, and identify the x values being sought. Second, if you're using technology, refer to the instructions at the end of this section. If you're using Table A2, refer to the body of Table A2 and find the area to the left of x, and then identify the z-score corresponding to that area. Third, if you know z and you must convert it to an equivalent x value, use the conversion formula by entering the values for the population mean mu, the standard deviation sigma, and the z-score found in step 2, and then solve for x. We can solve for x using the following formula. X equals to mu plus z times sigma. This is a form of the conversion formula. And finally, part 4, refer to the sketch of the curve to verify that the solution makes sense in context of the graph and in context of the problem. Let's consider this example. When designing equipment, one important criterion is to use a design that accommodates 95% of the population. Let's say that only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow for the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that the heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there also be a minimum required height? Why or why not? Let's start with step 1. The figure shows the normal distribution of the height x that we want to identify. The shaded area represents the shortest 95% of women. Let's use technology to find our value of x. For example, we can use Excel to find our x value. The first step is to enter your probability, mean, and standard deviations into your Excel spreadsheet. You can see that I have those values entered into cells B3, B4, and B5. Next, just select cell B7 and then go to the Formulas tab at the top. Then click on More Functions. Next, click on Statistical and then select the function norm.inv. When the function argument box pops up, assign the cell to each of the corresponding probability, the mean, the standard deviation. In this example, the probability value is in cell B3, the mean is in cell B4, and the standard deviation is in cell B5. You can see that the function argument box displays the value of 68.47007552 inches once you have those three values filled in. We can round that value off to 68.5 inches. Now, let's use table A2 to find the area that represents the shortest 95% of women. We will search for the area of 0.9500 in the body of table A2. The area of 0.9500 shown in this graph is a cumulative area from the left and is exactly the type of area that is listed in table A2. In table A2, we find that the area of 0.9500 is in between the two areas of 0.9495 and 0.9505. You'll see there's an asterisk, and in the footnotes it indicates that the area of 0.9500 corresponds to the value of z equals to 1.645. Now for step 3. Recall that our z-value is 1.645, our mean is 63.7 inches, and our standard deviation is 2.9 inches. We can solve for x by using the conversion formula x equals to mu plus z times the standard deviation. So we can say that x equals to 63.7 plus 1.645 multiplied by 2.9, and that is equal to 68.4705 inches, or when we round we can say that x is equal to 68.5 inches. Now step 4. The solution of x equals to 68.5 inches is reasonable because it is greater than the mean of 63.7 inches. An interpretation of our results could be a requirement of a height less than 68.5 inches would allow for 95% of women to be eligible as a U.S. Air Force pilot. So there should be a minimum height requirement so that we know that all the pilots who are eligible can easily reach all of the controls. This is the end of Chapter 6, Section 2. This is all we'll cover this week. Next week we will cover Chapter 6, Section 3 and Section 4.